This recording is for CTI 120 networking class, and we are now going to be on Module 6, which is Layer 3 networking. And this is technically Chapter 8 out of this particular book. So yeah, a little confusing. We're in Module 6, Chapter 8, Layer 3. Okay, so our learning objectives basically are to talk about networking protocols and routing protocols and how these things work together to get data, from one LAN to another LAN, and kind of how this thing works. Okay, logical addressing, that implies IP address. You can go into your computer and you can just type in a new IP address if you want to. That's changeable. Unlike the MAC address, which is burned into your computer, you can't change that one. Now, if we have an IP address and we need that IP address to get to a different network, then it's going to have to go through a router. Inter-network, that means between networks, routing. Now, as we are sending information down the line, it's going to get fragmented because our data packets can only be but so big, 1,500 bytes. And so that means that big files are going to have to get divided up into thousands of packets and sent, and those packets are liable to arrive at their destination not in order, and some of the packets may not make it all the way across the network intact. They might have to be resent. But that's okay because TCP has error handling built in, and so it's going to take those packets, make sure each one has arrived intact, and then it's also got sequencing information so that it can put the packets in order once they arrive where they're supposed to be. Okay, now network layer. Layer 3 is the network layer. This is where routing happens. Layer 3 has got your IP addressing information, and what we're trying to do is make sure that data gets from the source IP address to the destination IP address as quick as possible and as intact as possible. Now, there are multiple Layer 3 protocols, but most of those are defunct now. Back in the day, Novell had their own version of IP called IPX, and they were trying to get everybody to use their protocol, and for a while it was kind of working. There were some games out there that if you wanted to play multiplayer, you had to have an IPX protocol stack in order to make that work. But IP prevailed, and so that's what everybody uses now, and it's not called the Internet Protocol for nothing. That's the protocol you have to use if you want to traverse the global internet. And okay, Layer 3 switches and routers are similar but different, but for the time being, let's just pretend like routers and Layer 3 switches are the same thing. And they do primarily fulfill the same job. What they're doing is determining where packets need to go based on their IP addressing. Layer 3 switches do that just like routers do, but Layer 3 switches are just a lot faster. Excuse me. Okay, now a routed protocol is like IP. Okay, IP is going to get routed. Now, in order to make this happen, we also have routing protocols. Now, routing protocols are not important for end users. They don't really care as long as they get to watch their video or listen to Spotify or whatever it is they're doing on the internet. But as network engineers, this winds up being important for us because we're the ones that have to program the routers and switches and make sure everybody can communicate like they're supposed to. Now, a routing protocol. This is what routers use to communicate their routing tables to one another. So routing information protocol is an old one. That was the original routing information exchange that we used, but it had some limitations. It used a lot of network bandwidth, for example, and it wasn't very fast to converge. Now, open shortest path first. As its name implies, this is an open standard, So whether you're running Cisco equipment or Wellfleet or any other kind of equipment, it doesn't really matter. You can use open shortest path first because it is an open standard. And this is a protocol that's used in an intranet where you are the manager of all the routers, and OSPF is a fairly quick converging protocol, and it's more efficient than RIP or RIP v2. Okay, a routing table. Routing table basically is just like a database of networks and the router ports where that network resides. And a routing table can get kind of large depending on how many routers you have in your facility. And the routing table entry typically will consist of a network address and a subnet mask to go along with that network address. It'll have forwarding address. In other words, if there's a network that we don't control, which router port do I go through to reach it? So you're going to have, with every network, you're going to have a next hop router that I'm going to use to send traffic to that network. And then we also might have a routing metric. A routing metric is like a cost number. The slower a network link is, the higher the cost is going to be associated with that. So if you've got like a 10 gigabit line, that's going to have a much lower cost than a 100 megabit line. And routers always choose the lowest cost, unless you've messed up the programming somehow. Now, if you look at a Cisco router and you type in this command, show IP route, okay, it's going to tell you which routes or which networks we are currently aware of and how they're connected. So right now, we know about the 10.44.0.0 network. Okay, there's one subnet associated with that. 10.44.192.0 is directly connected to us, probably on interface 10.44.192.1. That's probably our address. And we also know about the 192.168.1 network. But in order to get to that network, we have to go out another router's port. So if we want to get to the 192.168.1.0 network, we don't have a direct connection to that, but we know about a router that does. And that router has an address of 10.44.192.2, which is a directly connected link to us. Okay, now routing protocols versus routed protocols. A routing protocol kind of gets transmitted in the background. It's not something that you have to manually send. It's going to automatically get transmitted out whenever there's a change to the network, or every, say 5 or 10 seconds, depending on how you've set up your router. Now, the routed protocols are the ones that actually are carrying the data. They've got the network addressing. Okay, and path, okay, if we're going from host A to host B, well, there's only one way to get there. We're going to have to go, okay, we've got a switch, and our switch faces router A. So as long as we're just talking on our own local area network, we can talk to the other hosts that are on this particular network. But if we want to talk to host B, then we're going to have to make a little trip. Router A knows where router B is, and also host B. So router A says, okay, I know how to get to host B. I've got to pass this traffic to router B. And router B sees the traffic and it says, oh, okay, that traffic belongs to one of my networks. I'm connected directly to network 3. So I'm going to send that traffic out this line. And then whenever there's a response from host B, it's going to go the exact same rigmarole going back towards host A. So even though these computers are on completely different networks, they can still communicate. provided these routers are set up correctly. Okay, now there might be multiple paths to go to the same place. So if there's a computer up here and it needs to talk to a computer down here, well, okay, so we've got a connection to this router, and then this router has a connection to this router. And so we can just send our data along this route here, and then this router can serve it out to the network because it's got a connection to it down here. Now, it's possible that there could be a problem in here. Like, what if somebody comes along with a pair of scissors and cuts this line? Okay, well, now our traffic has to go around by an extra router, but we can still get where we need to go. And this is kind of how we set up our networks. We try to make sure that we have at least one backup route for any data that's traveling around our network, because stuff does happen. There can be problems on the line here, and then we still have like a backup route we can take. Okay, some routing metrics that we use. Hop count is just the number of routers I'm going to have to traverse to get from host A to host B. Maybe there's only one router in between us, or maybe there's 50 of them. Don't know. Okay, but the hop count is something that the routing table has to keep in mind whenever it's determining which route for this data to take. The other thing we have to worry about is bandwidth. What if we've got a line that's only 45 megabit per second? Well, we don't want to use that unless we absolutely have to. We would rather use gigabit links or multi-gigabit links, fiber optic cables, that are long haul. The other thing is load. Wonder if there's a lot of traffic on a particular line. Well, maybe it makes sense to go by another route that has more hops, but right now it doesn't have as much traffic, so our data can get through quicker. There can be delay on the line. There's always going to be some kind of delay. Depends on how much traffic the router or switch is handling right this minute. And also delay can go back to your bandwidth. If you have narrow bandwidth, then you're going to have a lot more delay. Reliability. Some links are definitely more reliable than others. Like if you have a hardline fiber connection going, from like Wilmington to Burgaw, then that's going to be very, very reliable. It's going to be up pretty much all the time, barring some kind of disaster. But other links aren't so stable. Like, for example, if you're going through a satellite link, sometimes those work really fast and sometimes they're dog slow. It just depends on how much traffic you're competing with and also what is the weather like today. Maximum transmission unit, that refers to the maximum amount of data a packet can carry. And then also cost. Now, cost isn't in terms of like dollars. Cost here refers to one of the routing metrics that OSPF uses, and that refers to like the relative speed of a given link. And remember, faster links have lower costs, so it's like an inverse relationship. Okay, this business about convergence. Anytime there's a change to the network, like we install a new router or we take a router out of service, anything like that happens, or if we're like, say there's maintenance going on in the building and we have to, shut down an area of the building for a while, well, the routing tables on all the routers in our autonomous area are going to have to realize that, okay, there's a router down or there's a new router added. Now, how fast does that information propagate so that all the routers are now in sync? Okay, now if you just have like 2 or 3 routers, then your convergence probably takes place very, very quickly. But if you have a network like Cape Fear does, where we have routers not only at the North Campus, but also downtown, Burgaw, Surf City, so if there's any kind of change, convergence is not achieved until every router on the network has the new updated routing table. In other words, all the devices are synchronized. Now, load balancing is the idea where you have a router that has multiple links to the same destination, and it can put part of the data down one line and part of the data down the other line, and then TCP will reassemble the data in order when it gets to the other end. So if you have like two 1 gigabit links, then load balancing will allow you to basically use that as if it was an aggregated line and have effectively 2 gigabit per second transmission and receive speed. Now, access control lists. ACLs are a methodology that we use primarily for security. What an access control list does is it allows you to tell a router or a switch to either allow or deny certain kinds of traffic, and also to allow or deny certain devices. So you can actually take a switch port and you can tell it that, okay, here's the MAC address of the device that's going to connect to this port is going to be this. And if anybody tries to unplug that device and plug in another one, like say there was a hacker and he was trying to break into your system, and so he was unplugging a desktop computer and plugging in his own laptop device instead. Well, an ACL will now reject that traffic. He won't be able to join the network at all because the ACL says, okay, if your MAC address doesn't equal the one that I'm supposed to be servicing, then you can't use my switch port. So it's a good way of maintaining control of your system. And you can also tell your ACL to not respond to any ping requests. You know, you can tell it to deny HTTP requests, whatever you want to do. It's very flexible. Packet forwarding. Now, by default, we're going to forward all traffic, you know, if it's a network that we know about. And packet filtering, like we were just talking about, the network can block IP packets from going in and out of that network, you know, depending on who sent them or what is the nature of their traffic. So we could tell our switch to deny UDP traffic, which would prevent anybody from showing like videos over this particular switch if we wanted to be mean to our users. Okay, LAN to LAN routing. This is where you have two local area networks and you have a router in between, but a lot of times we're going to the wide area network. So we're going to go from our local area network through a border router out to the World Wide Web, because we like to do online shopping and stuff like that. Okay, now link state routing protocols. These are all modern routing protocols use this methodology. Link state not only keeps in mind how many routers are between me and my destination, but also what is the condition of those routers. You know, are there lines that we know about that are down or bogged down with traffic right this minute? You know, maybe we should send our traffic, instead of sending our traffic through the hub in Raleigh, maybe we should send it via Charlotte for the time being. This is the kind of thing that happens in the background. Like I said, the users don't have any clue this is even going on. But as network engineers, you know, this is our bread and butter. You know, we want our customers to be happy. Now, distance vector protocols are not quite as good as link state because they really only know about, you know, how many routers are between me and my destination. So if I've got one link that has 5 routers and one link that has 2 routers, well, I'm generally going to take the 2 router direction, even if the path going around that has 5 routers is actually a faster way to go. You know, because maybe they've got better technology, they've got fiber optic links that are very high bandwidth. But distance vector doesn't take that into account. It just looks at the number of hops. Which is why modern routing protocols are typically all link state protocols. Okay, link state advertisements. This says, okay, well, here's my routers, and ordinarily I've got multiple paths, you know, that I can take, but except for right now I've got a broken link right here, which means that any kind of data that's getting, like say from, you know, router C to router A, Well, ordinarily it would have two paths that it could take, but now it's only got one. All the traffic's going to have to go this way. Now, exterior routing protocols. There's really only one exterior routing protocol. This is going to be BGP, Border Gateway Protocol. There's a couple of different flavors of BGP, but that's what you use when you leave your premises and go out onto the internet. Now, inside the building, like here at CFCC, whoever's in charge of our network, they can use any kind of routing protocol internally that they want to. Now, a lot of guys use EIGRP because it comes free with Cisco routers, and it's a good protocol, and it's basically already set up for you. You don't have to do a whole lot with it. But if you've got, like say you've got routers on your premises that were built by multiple companies, maybe you've got like Juniper and Cisco, maybe some other companies, and you need those guys to be able to communicate with each other, then you're going to need to use OSPF. But these are interior gateway routing protocols. So interior protocols can be whatever you want. Exterior protocol is always going to be BGP of some sort. Okay, RIP is a fun one. This is an old school protocol, but it's still available. If you wanted to use RIP, then you could. You just tell your router to use RIP protocol. Now, here's the thing about RIP. RIP is bandwidth intensive because every few seconds it sends out a copy of its entire routing table. So it winds up eating up a lot of bandwidth. Now, if everything on your system is gigabit, then maybe you don't really care because it doesn't make enough of a difference. So you're not really worried about it. However, if you're limited in your bandwidth and RIP is using up a lot of that bandwidth, then you might want to stop it and use something like EIGRP. Now, whenever there's a change to the routing table on one of the routers, it's going to broadcast its entire routing table to the whole network. So newer routing protocols like EIGRP and OSPF, whenever they sense a change in the network, all they send out is that change information. They don't send their entire routing table. So they're much more conservative with bandwidth. Okay, now routing loops. If you've got multiple routers that are connected together, and this is not going to be a problem with modern routers because engineers know about this. Excuse me. But if you've got traffic that's going out one router, it's possible for the traffic to wind up getting passed around and around and around and never get to its actual destination. But the software has preventative measures in place to keep this from happening. So you should not ever have to worry about a routing loop. Excuse me. Okay, RIP version 2. This came out in 1998, and it was an improvement over the original RIP. OSPF was even better. Interior Gateway Routing Protocol. This was Cisco's proprietary protocol. I can't remember what year, but at some point they made this an open source. They basically made the code for IGRP available to other vendors if they wanted to use it. Now, enhanced IGRP, this is what Cisco likes to use now. This is kind of like their default routing protocol for their equipment. And this one is not public domain. This is still a proprietary protocol. And then BGP is an open standard that everybody uses, and BGP is the protocol of the internet. So if you're setting up a wide area network and you need to talk to somebody else's network, you're going to be using BGP to share your routing data. Okay, resilience. If you just got one router on the network, then that is a single point of failure. If something happens to that router, then you're going to be restricted to LAN traffic only. So no more accessing the internet for you. Now, in order to keep this from happening, any engineer worth his salt is going to make sure that there are multiple pathways out to the internet and that we have routers that are kind of watching each other's backs, so to speak. And so this is referred to as redundancy. We have, and there's such thing as you can have a hot standby or you can have a cold standby. A hot standby router is one that is plugged in, it's connected to the network, it's up and running, and it's using hot standby router protocol, HSRP, cleverly enough, to monitor the router that's actually handling traffic in and out. Okay, and if it senses that the primary router is offline, then it can instantly take over without human intervention. Okay, that's the idea of hot standby. Now, there's also such thing as cold standby, in which case, like say I buy a router, but I don't just buy one router, I buy two routers. And I go ahead and configure them up identical. For all intents and purposes, they are like copies of one another. And one router I put in service, I go ahead and plug it into the network and get it up and running, and now everybody's using it. The other router, I put it back in the box, I put it in the closet. Now, if something happens and my primary router has a problem, it needs to be fixed or whatever, what I can do is take the router out of the closet and hook it up to the network and turn it on and take the old router out of commission. Okay, so that's the idea behind cold standby. Now, something else you might need to do for your system's resilience. I really like power supplies. Now, there's some systems, like servers especially, like the ones we have in our server closet, a lot of those have two power supplies. And one power supply is, providing power for the server. The other power supply is sitting there running like in standby mode. So if the power supply dies, then the backup power supply can just automatically take over. And those power supplies are both built into the cabinet of the server. Now, something that's kind of along those lines is battery backup and UPS. A UPS is a device, and you guys may have these at home. I know my computer at home, I've got it plugged into a UPS so that if the power ever does get cut out, then my computer doesn't just crash, right? Because I don't want that to happen. And I've got a UPS on my cable modem, and I've also got another UPS on the TV that's in my living room. I don't really need to have a UPS on the TV, but it's come in handy before, like especially during storms, whenever the power's glitching, the UPS makes sure that the TV has a good, like a steady signal and is not as susceptible to stuff like lightning damage. Big businesses will have not only battery backup, but then they'll have diesel generators that back up the batteries so that, if the system's been on battery power for more than like 1 minute, then the diesel generators will automatically kick on and start powering the entire facility. So if you ever go out back of the hospital at New Hanover, you're going to see the physical plant back there. There's like a big, huge building, and there are diesel generators in that building, and those things are kept primed and ready to go at all times just in case of a storm. Because, people that are in the hospital need electrical devices to stay alive. Now, sometimes we actually have like a backup router that's already in place, or we might actually have like a virtual router set up. I'll show you how that goes in just a minute. We can have backup switches, basically everything on the network. We don't want to have any single point of failure. If you look at your network and you're like, okay, if this switch goes down, then we're going to lose like half the campus. Okay, well, that's not good. You need to figure out a way to have like, multiple switches, at least one other switch that can handle the load if the first one is somehow out of commission. First hop redundancy protocols. These are protocols that can support the resilience of a network, but depends on the configuration of the router and the links that the router is connected to. What you can do is you can connect multiple links of the same capability, and you can use load balancing like we were talking about a few minutes ago. And then there's a couple of other first hop redundancy protocols, VRRP, which basically takes multiple routers and gives them like a single virtual address, so that the hosts on the network, the PCs and stuff, they use the virtual IP address, even though the actual IP address of the individual devices is different. And that way, if one of the devices goes offline, then the hosts don't notice because they've been using the virtual address anyways. And then there's also the HSRP, Hot Standby Routing Protocol, and told you guys a few minutes ago about how hot standby works. You've got two routers, and one's actually handling the traffic, and then the standby router is just sitting there monitoring the live router and will take over in case it fails. And this next picture, okay, this shows you the idea about the virtual router. Okay, so we've got, and you set this up on both these routers. These routers have to be configured basically identically, except for they have different actual IP addresses. So this guy's got an IP address of 10.1.1.2, and this one is 10.1.1.3. But we've told both routers to present a virtual address of 10.1.1.1. Okay, so whenever these computers over here come on the network, their gateway address is going to be 10.1.1.1, and that's what they're going to send and receive traffic, using that gateway. And as far as these guys are concerned, the virtual router is the router. They don't really care as long as their traffic's getting in and out of the network. Now, the virtual router is going to send its traffic through one of these guys to the network, one or both, depending on how we've got this thing set up. And then if one of these routers goes offline, like you can imagine, if all of a sudden this router died, then the virtual router doesn't get affected. It's going to send its traffic through the backup router. Well, let me see. Okay, so that basically is it for this chapter. I've got you guys packet tracer activity that I'm hoping you're going to be able to look at those instructions and follow them. I will make a video walkthrough of that packet tracer so that you guys can kind of see how it goes. I made a video about how to obtain packet tracer and install it, and how to, hook up some basic devices to a switch. I think once you get started with packet tracer and you play around with it a little bit, you're going to enjoy it, because it's actually kind of fun, to see, okay, how many routers can I chain together, and how many switches can I plug in. Of course, the more complex your network gets, the harder it is to keep in mind, like which routers are doing what. Okay, so I'm going to go ahead and post this up to the internet, and I'm going to give you guys a link, and then I'll see you in the next one.